Hi, welcome back. Today we're going to be talking about the calculus of parametric equations. Before we begin that, though, I would like to review a little bit about parametric equations that you learned from last year in pre-cal. You might recall parametric equations are very useful in analyzing motion. They allow us to describe the motion of a particle in terms of an outside variable. In other words, not using x or y, but in most cases, we use the variable t, and that is what we call a parameter. In other words, we can represent both the vertical and horizontal position of an object or particle independently from each other. And now we normally will say x is a function of t, and we would say y is a function of t. And you might remember this from last year. You said your teacher would say, well, here's a function y equals x. Write this as a parametric. You would say x squared, let's say. X is t, then y would equal t squared. And now what happens is, where originally y was a function of x, now both x and y are no longer dependent upon each other, but they're dependent upon this outside variable, t. And that's what we call a parametric equation. In other words, this is where x and y are independent of each other. In other words, what this is saying is, instead of being where, in our case right here, where x is dependent, or the independent variable, y is the dependent variable, here we're saying both x and y are both dependent variables in this case. They both depend on t. Therefore, we can give any point or locate any point with the coordinates f of t, g of t. Now, sometimes we will use x of t and y of t, mainly so we don't get confused with the lettering and everything. So f and g are what we call parametric equations. They are in other words, they are two equations that are independent from each other. Next year in multi, of course, we'll say a third variable as well, a third equation as well. But that's next year. Two equations independent of each other, but describe the position of a particle along a curve in terms of its x and y coordinates. Later on today, or tomorrow, depending on how far we get, we are going to discuss how to describe the motion of the particle using parametric equations. And parametric equations are very nice because they can define non-functional relationships. Like, for example, I have this graph right here. This is clearly not a function because it will fail the horizontal line test. But we can use parametric equations to describe the motion along the particle itself. And it also will give us direction, which we're going to review in just a few moments. So if we're along this particle here at t equals 0, we start at this point, and as we move along, and at any given time t, we can find the position by plugging in t for x and a y component. It's really useful to think of t as just being like a time component. So let's take a look at an example. So let's say f of t, g of t is given by this point right here, where f of t, they're telling me, is 3t plus 1, and g of t is sine of t. So in other words, here they're telling us that this is indeed a parametric equation, and this is going to give us our x coordinate at any given time t, and this part gives us our y coordinate at any time t. We want to find the position of the particle when t is 0. So the first thing we want to find is the x position at 0, and they're telling us to plug it in here, f of 0, and that's just going to become 3 times 0 plus 1, which is 1. To get the y position at 0, they're telling me to plug it in for g, and again, you'll see me just use x and y most of the time. And this is going to become, of course, sine of 0, which is 0. So the position is going to be at the point 1, 0 right there. Very easy to do. So kind of a difference up here. So let's take a look right here. Obviously, this can give us a function. But let's talk about what the difference is between the function of a graph and the parametric equation. So let's talk real quick about that. What does a function give us? Well, a function will give the shape of a graph. And I compare like this. So a function will give the shape of a graph. For example, think of a sidewalk. You're walking on a sidewalk. The sidewalk represents the function. Well, then what does the parametric tell us? Well, the parametric doesn't give us the shape of the graph. It gives us the path along the graph. Oops, sorry. So this is going to give us the path along the graph. In other words, if you go to our sidewalk example, for example, this represents our sidewalk, the path is saying it's gonna tell us how we are moving along the sidewalk. What direction are we moving? And so on and so forth. So a function and a parametric are going to be the same thing, but think of it like this. If you can look at the graph right here, you can see the sidewalk. But let's say you couldn't see the sidewalk. You can only see the person walking along that sidewalk at various points. That's a parametric. And you can plot out those points. So like I said earlier, normally we'll write f of t, g of t as x of t, y of t. That's just to kind of make it a little bit simpler for us. Parametrics are a big help. We see these a lot in physics and other application problems. They allow us to view a particle's motion in terms of its individual components, such as height and distance. So if I have, let's say, a particle moving on the xy plane, ready? If it will allow me to get the position at any, let me redo that again here, can't do that right. It'll allow us to give us the position at any given time where x and y are independent of each other. And we see this in physics. For example, I can get my horizontal position and I get my vertical position independently from each other. I can't remember those physics equations. That's physics teachers. But anyways, if you go to video number 2, we will take a look at a little bit more review from last year in pre-cal. I will see you then.